Minsum decoding, we start with basic understanding of why product of science is taken. So, when we reach the product of science, we will understand why product of science are used to message passing, for message passing. First of all, magnitude means how much confidence we have in the bit. For BPSK, plus 1 means 0, minus 1 means 1, binary 1. So magnitude, if is reduced, for example plus 1 due to noise reduces to 0.5 or zero point 0.4, then the confidence is lowered in the bit. Due to noise, the bit has reduced its magnitude and thus its BPSK modulation of plus 1 is less emphasized as plus zero point 0.5. Similarly, if minus 1 deviates from its value towards 0, then it is going towards positive side, which means it can infer that it was a bit 0, and less confidence is there in claiming it as bit minus 1. We can draw this and show this also. There is the center line. This is the BPSK modulation. Phase 180 degree out of phase is shown, and binary 0 and binary 1 bit is represented by these two numbers. And when noise affects this plus 1, which indicates a 0, might deviate here or there. If it deviates on the left side, as I said, if it reduces to plus 0.5, then we have lowered our confidence in saying that a 0 was sent, coded as plus 1. BPSK modulated, not coded. Now, positive LLR. What is positive LLR? A positive LLR means that we have a 0. A negative LLR, log likelihood ratio, means that it is 1. Log likelihood ratio is ratio of probability of a bit being 0 versus the probability of bit being a 1, the likelihood of these two bits. I have explained in previous video with a slide. With this slide I have explained what is log likelihood ratio and why log is taken, so that division becomes simple subtractions, easy for computer systems to compute, and how it is practically mentioned. So we start from LLR with our previous knowledge, and we have these equations. These are called parity check equations. They should sum up to 0 for even parity checks. Now with these four mandatory conditions, we say that, let us say that we have a parity check equation and two of the bits say that they are 1 and they are 0. How? The LLR received from channel is channel indicator of this bit is minus 0.5, which is a little less confidence in saying it is minus 1 BPSK modulated, which represents a bit 1, and LLR plus 2 strongly says that it is bit 0. So these two LLR, when they are in a equation like this, say V2 is this and V3 is this. V2 is saying I am 1 and V3 is saying I am 0. So 1 XOR with 0 gives a 1. That means V1 should be 1. So these two bit nodes send this bit node during this check equation check node. This check equation is called a single check node. These two bit nodes, column nodes, tell this one to be a 1. Why? Because when this is 1, then 1, this is 1, and V2 is 1, 1, 1 is 0, and this 0 XOR with 0 will become a 0. Equation is satisfied. That means the parity check equation satisfies, and the equation is correct. That means these 3 bits are correct. So that's how the message passing should work. Now, how this message passing will work? How will these 2 bits tell V1 that it should be 1? Look at the signs. If we multiply the signs of these 2 bits, they give a negative sign, and negative is indicator of 1. So multiplying the signs tells the bit what bit it should be. So what 1 should be? It should be a 1, and it is 1 in BPSK modulation. If we multiply the sign of these two LLRs, then it indicates a minus, which indicates that it has to be a 1. Similarly, other cases also it will indicate the correct bit. So plus into plus is plus, and minus into minus is plus, which is a correct indicator of the bit, the message that is passed on by 2 different bits to the third bit. If there are only 3 bits in an equation, as you can see, we have a parity check equation which has got 3 bits. In these 3 bits, you have to notice that 2 of the bits will tell the third bit what it should be, so that the parity check equation is satisfied. So in all the cases, we have understood that multiplication of the signs of the 2 bits gives a sign that indicates what binary digit the third node, column node, or bit node should be. So we begin with the example. Suppose this is a H matrix and this is the received LLR. Now, having an H matrix and received LLR, this is the H matrix. Crosses show positions of ones, and absence of anything means it is 0. So this is the matrix, parity check matrix. This is the parity check equation. The parity check equation says V1 XOR with V2 XOR with V3 should give us 0. And parity check equation 2 says V1 XOR with V4 is also 0. We have designed these equations so that they satisfy this even parity check rule. Similarly, parity check equation 3 says V2 XOR with V3 XOR with V4 equal to 0. These are bit nodes, the column nodes, and 3 equations will tell you what V1, V2, V3 should be, V1, V4 should be, V2, V3 and V4 should be. All different checks will help us find out what actually binary digits, 4 different bits were sent. Initially from the receiver we get these signals. This is BPSK modulated signal. +1 represents a 0 binary digit, -1 represents a 1, and plus again 0 and a 0. So this received signal says that a 0 1 0 0 has been sent. Now based on these deviated noise affected values, we will start decoding using the MinSum algorithm. In the MinSum algorithm, initially these LLRs are directly copied to the position of ones. So this LLR is copied directly here, this LLR is copied directly here, and this LLR again is directly copied here, only in the position of ones. So this becomes this one 1, and V2 becomes -0.5 like so, and +2 is copied here. So first 3 bits are copied due to first 3 presence of ones in the parity check matrix, and similarly the outside bits V1 and V4 get copied exactly as LLR. So this is called initial V2C matrix. Now the decoder performs parity checks by demapping the BPSK. Straight away the indications are that this is 0, this is 1, and this is 0. So this is 0, this is 1, this is 0, and parity check equations, two of the equations fail and one passes. The one passing equation indicates that V1 and V4 are correct. V1 is 0 and V4 is 0. So this equation is trying to tell you that V1 and V4 bits are sent correctly or received correctly actually. Not sent. Sent is already ensured by the transmitter. The receiver has to check if the received bits are correctly transmitted. So the second parity check equation checks out, indicating that V1 and V4 are correct. Now in first equation, message passing has to be done so that this the equation is not checking out and it has to be correct. So how it is done? V2 and V3, when they are XORed, they say that this V1 should have been a 1, because 1 XOR with 0 is 1, and then 1 XOR with 1 would have been a 0. But here, due to this 0, it is not checking out. The equation is wrong. So that's why these two V2 and V3, where are the bits? V2 and V3, these two bits say that V1 should be a 1. So, and then this equation checks out. How this message passing is done? Again, as we decided in the previous slide, we have to multiply the signs of the two bits. So sign is minus and sign is plus. Minus into plus is minus. So minus is indicating that this should be a 1. So V1 should be a 1. So this is explained. This is the message passing part of this algorithm. Now the sign indicates that it should be a 1, and in row 2 again it is correct, so no message passing is required. But how the message is passed, it is passed correctly, so that equation is checked. It is written here. In row 3 also similar operation will happen. Now how about passing the message? What message is passed? We pass the minimum, least suggestion. So amongst these two values which are here, minus 0.5 and plus 2, the minimum value is passed, so that minimum deviation is given. A very slight hint is given to the, without disturbing the equation too much, only a small magnitude is sent. So this is chosen. Out of minus 0.5 and 2 plus 0.2, the magnitude 0.5 is less, so magnitude 0.5 is chosen with the correct sign. Sign is minus. In the next slide, we will see that happening. So there it is passed. So the first equation says that it should be a 1, which is sign minus, and the magnitude is the minimum of these two, which is 0.5, is sent and copied here. Similarly, it is done for this one. These two will tell what this should be, and the minimum magnitude with the sign is sent. Product of these two signs is plus, so plus affixed here, and magnitude minimum of this is this, which is here. Then this one is sent with these two indicators, V1 and V2. Product sign is minus, so minus is affixing here, and the magnitude of this one is smaller. That's why it is called min sum. Sum is understood later, but in C2V matrix update, minimum value is passed. So these signs are computed using our multiplication method, which says what bit it should be, 0 or 1. So this is for BPSK modulation, and minimum value is passed, so that minimum change to the equation is done without disturbing it too much. A slight indicator is better than a large indicator, which might overthrow the result to the wrong side. So this explanation tells how this summarizes how this is done, and it is called C2V matrix update. Check node to bit node information is sent. So it says V2 and V3, out of them minimum value is used, and sign is product of their signs. That's how V1 is updated, and others are updated in the similar manner. Now C2V matrix is updated, then V2C matrix is made. How is it made? Here the simple summation rules takes place. Now we want to indicate what are the bits in these four positions. These are the initial LLRs which tell this 0 1 0 0 is sent, and we will find out by probability this method with what were the bits actually. So we will sum up these columns in V2C matrix update. Now before we had check node to bit node information being sent. Here bit node to check node information will be sent. This bit will send information or gain information from these three and find what this bit is actually. Is it 0 or a 1? At this receiver side it says it is a 0. So how this V2C matrix is updated? We use the channel LLR, which is this, or in this initial matrix channel LLRs are present. We have this channel LR V1. Then in this channel LR, the C2 node tells this what it should be. So actually what happens is the LLR, which is +1, which is here in the initial matrix, we are trying to find out the correct value for this position. We will have the LLR added with the value which is here in C2V matrix. So this position, if you want to update, we have the LLR, initial LLR, the initial matrix value plus the value which is here. No value here, so 0 and plus 0.2 here. So this is added to this and we update it in the V2C matrix. So it is summing up the columns to confirm or to move this value, the LLR value, towards the more probable or correct estimate of the received vector, what it should be. Similarly, when we update this in V2C matrix, we use the channel LLR here, which is +1, and +1 when added with the other column entries at the other check nodes will give you the correct value. So +1 minus 0.5 will give you +0.5. Similarly, to update this value, we'll take the channel LLR and add the other side, the other check nodes informations. So this bit node is sending information to check node, that's why V2C matrix. So we will have this one updated as -0.5 plus 1, which is +0.5, and this one as -0.5 plus 0.2, which is -0.3 as this one. Similarly, others are updated. So this is how V2C matrix is generated, and this will become the initial matrix in the second iteration. This is just the first iteration. If in the first iteration we want to stop the decoding algorithm, we will compute the final belief. To compute the final belief, we will list the initial LLRs and then we will add the column values as I am indicating here and add them to the LLR. So this has become initial matrix for the iteration second, and based on C2V matrix the final beliefs are calculated using the initial LLR value, summing up with the whatever the magnitudes we have in this column. These are two are there, they are added, and then they are added to the initial LLRs to give the total belief. So this is the total belief, and this is hard decoded to the final values. Now this is the estimate or the message hat received in first iteration. If we do not stop it in first iteration, in second iteration, this matrix will serve, this matrix which is built using initial matrix and the C2V matrix, this will become the initial V2C matrix. So in the next slide we do iteration second, and you notice that this matrix is copied directly here, and this matrix will be used as initial matrix, and then again these two will be computed, and in second also, if we want to conclude, that this matrix will be used to compute the final belief. So let us do it in short summarized way. This is the initial matrix. After then we compute C2V matrix. C2V matrix is computed like this. This one will be indicated by these two, sign will be minus, and the minimum will be passed, which is like so, 0.3 is the minimum. Similarly for this one, signs of these two is plus, so plus is affixed here. Minimum magnitude of these two is 1.2, 1.2 is here. For this one, sign of this is minus, minus is affixed here. Minimum magnitude 0.3 is here. So C2V matrix, this is not CTC, C2V matrix, it should be V. C2V matrix is made. After this matrix is made, we will sum up the value. This is message passing minimum, and sum will be done here. How it is done? Using this an initial LLR. For this we will for the initial LLR is 1.2, and we will add minus 0.3 to it, which will give a plus 0.9. Similarly for this one we will have plus 0.5, and then add minus 0.3, which should give you minus 0.2, but that is not here. So this has to be checked again. To check this again, let us go back here, and we have the initial LLR, this one, and this one summed up to give this one. This one to find this one, initial LLR is plus 1, plus 1, and minus 0.5 is plus 0.5. So these two are giving these values. Similarly this and this should give, this should be added with this one to give this one, which is right, and this should be added to this one to give this one, which is not right. Let's check the other column. This one should be, initial should be added to this one to give, again these values are not right. Let us check them, and when we want to give the final belief hard decision, we will use this matrix and the initial LLRs. So the initial LLRs should be like this. This will sum up to minus 0.6, minus 0.6, and this should sum up to plus 2.4, plus 2.4 minus 0.3 gives this plus 2.1. Similarly minus 0.6 plus minus 0.6 plus 1.2 should give you plus 0.6, which is correct. So this first row is taken as an initial LLR and summed with these columns. Again we'll check with this, plus 1.8 minus 0.3 is 1 plus 1.5, and plus 0.5 is 2. This is correct. 0 plus 0.5, this should be 1. So again this one is also not correct. This is 0, so this value is picked up. Minus 0.3, we have the topmost value, these are taken as initial LLR. So let us take this one, minus 0.3, this will be 1, and subtracted with 0.3, it will be 0.7, which is correct. So this part is correct, but calculation of V2C does not look right. We can check it again. This is, let us say, LLR, and we want to compute, suppose this is the place we want to compute for. So this is LLR plus 1.2 minus 0.3 should be 0.9, which is right. For this point we have again plus 0.2 and minus 1.3, again plus 0.2, because this is the LLR. Now I have got it correctly. Actually it is correct. Let us write the LLRs here, so that let us encircle the bits that will act as LLR. So I am encircling the bits that will act as LLR for the second iteration. Now if these are LLRs for iteration 2, let us now check if this matrix is correct. Initially we thought that this is wrong, but it is not. For computing this position, we will add this with this, which gives plus 9, and for computing this, we will add this with this, will give you 0.9. This is correct. For computing this position, we will add minus 0.3 to plus 1.2, which is right. For this position, we will add minus 0.3 plus 2, again 0.9, correct. For this position, we add plus 1.8 to plus 5, we get 2.3, which is correct. For this position we add 1.8 to minus 1.3, which is 1.5, which is correct. For this position we will add minus 0.3, 2.5, 0.2 is correct. For this position again same is to be done, and it is also correct. So this is correct, and this is how iteration 2 ends exactly in same fashion as iteration 1 has been done. And after reaching this part, if we want to stop at iteration 2 and do not want to proceed at iteration 3, we can estimate by hard decoding what we have. Here hard decoding is done by summing up these columns and with these LLRs. So this is minus 0.6 with sum with this is 0.6, which is correct. So these decoded values, these summed up values are now hard decoded, plus indicates a 0, so all of them are 0. Again the same decision is obtained in iteration 2 also, and this is how sum occurs. Minimum means in C2V matrix minimum magnitude is passed, and minimum magnitude is passed using signs, and sum is done using the sum of this column with the LLR to estimate the values of V2C matrix. This becomes initial matrix, and this is used, the column is used with LLR to conclude what belief we have in the first iteration. Similarly, the LLR sums with these to estimate the beliefs for this iteration. The more the number of iterations, the more refined the answer is.